Welcome to this review of the presentation that I will be giving at the Commercial UAV Expo in Las Vegas in a few weeks. Like always, any feedback or comments that you have are always welcome. So, what we will be covering today is the current limitations of drone usage as it relates to big data and enterprise data. We will be introducing some concepts that are probably new to many people in the drone industry, but not so new to people who are in Silicon Valley and are used to working with large data sets. We're going to define the impact of big data and why it's important for the UAS community to start thinking about this. And then finally, we'll be giving some use cases. Okay, so there's two classes of UAS operators out there. There's a lot of people who are kind of in the startup or enterprise startup position. So this ranges from everything from some guy in his garage with a high-end drone and is looking to go out and do stuff. It could be taking pictures of structures for real estate use to doing crop surveying or mapping of fields for farm use. But basically, one or two guys trying to make a buck. And then on the other end, the other range of the spectrum are the enterprise users. So, they could be anything from, electrical utility or water authority or any kind of corporate entity where maybe flying a drone and using it to collect data might be beneficial. And one thing that these all have in common is they're mostly focused on just flying the mission. And when I say that, what do I mean? Basically, they take their drone, it could be high-end consumer drone, like I said, out into the field, and they fly it over a structure and they typically take discrete pictures. They might be taking video. When they're done, they land the drone, hook it up to their laptop or their computer, and then they offload the data. This is a very time and labor intensive activity. On top of which, the data typically ends up on the laptop, and that's the end of the journey. So the analytics that are performed are typically performed visually by a human operator looking at the screen, either looking at the video or looking at individual snapshots and making a decision as to whether or not what they're looking at is good. Again, not repeatable. You take the same guy, different time of the day, maybe he had something different for lunch that day. He might come up with a radically different conclusion looking at the same exact data. On top of which, this doesn't scale well. So if you're operating a single drone and you're taking pictures in a field and you're then landing it and analyzing the data, if you get 10 more customers, there's no good way for you to scale up that business aside from getting 10 more expensive employees. On top of which, you're limited to the constraints of the UAS. So if your UAS has limited amount of memory and limited flying duration, you're kind of limited as to what the drone will let you do. So in general, this segment of the market is just not being served well. They have nothing to aid them in their quest to getting insights from the data, and they're kind of on their own. On top of which, the data is not enterprise ready. The data is offloaded to a laptop typically. Maybe it'll be brought back into the corporate office and they'll show people. Maybe they'll store the data somewhere on the enterprise system, but it's not a first-class citizen. A lot of times the data just sits on a laptop, and after several flights and memory becomes scarce, that data is just thrown in the garbage. There certainly isn't any formal way for them to say, hey, Joe took a scan of that cell phone tower 5 years ago. Let's pull it up and analyze it again. Nothing has really gotten to that point where they're thinking in terms of the big picture. And probably the most important thing is the flight profile is directly related to the success of the mission. If you are flying around and taking pictures of field and you're taking individual snapshots and you're hoping to get 60% overlap along the flight path and 70% overlap side to side as you make passes, you bring that data back, you load it up onto your laptop, and you're back in the office and you look at it and you realize that due to the wind shift, you weren't getting the overlap that you're hoping for, or maybe there was a structure on the field And since you took all of your pictures from the top down, you missed all the oblique angles, and therefore you really can't do what you were hoping to do. That's a terrible waste. That means that mission was a waste. The only way to recover from that is to go back out in the field and redo the mission. Very costly. On the other end of the spectrum, we have drones as a service. So there are quite a few companies out there, not naming any in particular, trying to keep this agnostic, but there are a lot of drones as a service out there, and they are using, on the low end, high end consumer drones, and on the upper end, purpose-built drones that are fairly sophisticated. And the way these typically work is the drone will take off, it will fly over the area that you want to scan, take pictures, videos, or still images, and a lot of times it will, upload these pictures on the fly or download them from the drone to a local station, or if there's 4 or 5G available, they will be able to send them over the internet to a cloud service provider. And then in that cloud service provider, they will analyze the images and give you a report. Now, this is great because it's scalable. You certainly can get done much faster. You're not beholden to downloading the data onto a laptop and doing your analytics by eye. It's easy to do that. And if you run the analytics again tomorrow with the same data, you'll get the same results, so it'll be very repeatable. A lot of times you are still limited to individual JPEG images, which could mean that you don't get the overlap that you are hoping to get. Although some are venturing into the 4K solid video end, a lot of staying away from that due to the sheer amount of data that gets generated once you start taking 4K video. The nice thing now is you are strictly limited by the endurance of the UAS and the data link. The images don't have to stay resident on the UAS. They kind of fly over the internet and get offloaded from the UAS. So as long as you have battery and as long as there is a link from the UAS to the internet, to the cloud, you can run your mission as long as you want. One interesting thing is that the results from something like this are typically brought into the enterprise. So you will get some sort of sensor report that you could download as a file or as an online report, and you can kind of suck that into your data warehouse and have that report handy. A lot of times, though, if the data is going straight from the drone to the cloud service, you won't see that data again. So that data will not be in the enterprise, and being up on a cloud service, it's really up to them to decide what's going to happen with that data. Do they save it in perpetuity or do they delete it after a certain amount of time? It really is a function of your contract. On top of which, there's a bit of vendor lock-in. So if you're working with vendor A and they do a certain type of scan, but vendor B comes along and they do something a little different, a little better, you're kind of locked in with vendor A. If you have a contract, you can't have vendor A send the data over to vendor B. So in general, we call this not an open source approach. You're kind of locked in. And finally, you still have the same issues that we had with the startups. The mission profile is a function of how well you will succeed. If you don't take enough pictures to get enough overlap so you can do your calculations, ultimately your mission will fail. Now, in a galaxy far, far away, big data is happening. So in the world, there's something else going on. It's called the internet, and the internet is generating lots and lots of data. So companies like Google, Yahoo, LinkedIn, Netflix, all of these companies have been dealing with collecting and storing petabytes of information. And that's unheard of. In the older days of relational database, you would talk about terabytes on the high end, and that's kind of where a relational database system kind of peters out. But in the big data world, they're collecting petabytes of data, and there's no end in sight. They're using an approach that lets them go even beyond petabytes. And that's the big guys. These are the guys in Silicon Valley who are driving this. But yet, Banks, healthcare, e-commerce, they're all feeling that ripple effect. They're all getting lots of data, and they're expected to not only store the data, but much more important, to get insights out of the data. So how much data are we really talking about? Well, in 2013, Gartner estimated that the size of the internet was 4.4 zettabytes. And that's the internet that you and I typically think about. We're not even talking about the dark net, which is this shadow internet that has a lot of other good things and quite a few bad things on it. And that the size of that internet was estimated to be actually 10 times bigger than the internet at large. But Gartner went on to say that by the year 2020, they felt that the internet would increase by a tenfold by 2020. So that's 44 zettabytes of data. They also estimated that at the time we were creating 2.5 quintillion bytes of data a day. And if you have trouble getting your head around that, 2.5 quintillion bytes of data is the equivalent of 10 million DVD discs, Blu-ray discs written a day. And if you're having trouble getting your head around that, if you took 10 million Blu-ray discs and stacked them one on top of the other, they would rise to the height of about 2.5 Freedom Towers. So that's a lot of data every day on the internet worldwide being generated. They also went to go on to say that by 2018 there would be 15 billion connected devices. And so what's a connected device? Connected device is cell phone, health meters, refrigerators, dishwashers, TVs, cars, jet engines, you name it, anything that's going to connect to the internet and send and possibly receive information is going to be considered a connected device. And why is that important? Because these connected devices can then get information about from other connected devices and make decisions to alter how they operate. In 2020, they estimated that number would go up to 50 billion. And at the time they did this study, the drone phenomenon had not hit. So there is little thought put into just how many UAS will be up in the air, connected to the internet and talking to things around them. So the bottom line is that streaming of data is coming to age. We are finding ways to collect data in motion, to perpetually store this data, to make actionable events upon the data. So as the data is coming in, these devices are doing things. We're coming up with ways to make decisions in real time. On top of which, the data that we're getting is no longer, quote, structured data. And structured data is the kind of data we would put in our database. But we're collecting structured and unstructured data. So what does that mean? That means, yeah, we're collecting relational type data, nice data that fits into nice types of columns. You can classify what each one is. But we're also collecting log files, emails, phone and voice recordings and streams, social media tweets. And all of this stuff is coming into a new type of system that allows the data to be stored together and processed together. And that's really, really important because historically, some data, structured data, would go into a relational database. Other data would be sent off to, like log files for a server, would just sit on a disk somewhere on some server buried in some back office. Emails would be on an email server in a somewhat proprietary database. You take phone and voice. Those would go to separate systems that had their own proprietary storage, binary storage, no real good way to search it. And corporate America has gotten or had gotten very used to wearing blinders. And we would talk about doing systems to process relational data. We talk about doing systems to process the data in our log files, to figure out what's going on in there. We might search through email. But nobody was thinking along the lines of, hey, I want to know what this customer's experience was like, and I want a nice, clear path of everything that happened with this customer, from where he went in my websites to what data he pulled out of the relational database to the phone call that he made to tech support. And on top of which, I want the sentiment. I want to know what he said on Twitter. I want to know what he said on the phone. Was he happy? Was he sad? What was the conversation like? That has not been something that corporate America would even consider, because just a decade ago, it was absolutely impossible. More likely, it was very, very difficult, but impossible is not an unrealistic word. The beauty now is we found a way, or Silicon Valley has found a way, to bring the data into the enterprise and keep it all together so that we can gain insights on the data. So why should you care? Well, many of these companies have dealt with deluges of data. They've also faced strict cost containment and cost reduction pressures. While the drone industry hasn't necessarily had cost containment issues, they're startups for the most part, and costs are an issue. So it should be interesting from that standpoint. The big thing is they've solved this problem for you. And the technology of choice is loosely referred to as big data. More specifically, it's referred to as Hadoop, although Hadoop is not the end-all and be-all of big data. But big data Hadoop, when you say that phrase, it kind of sums up, what it's all about. What it's all about is the data. While UAS people tend to focus on the mission, that is not where the secret sauce is. The secret sauce is about the data. It doesn't matter if it was collected by a drone, a manned aircraft, a guy standing on a ladder, or from a satellite. All we really care about is collecting sensor data. And once we have the sensor data, very amazing things can be done with it. So what you're looking at now is a typical block diagram for big data, in this case Hadoop. And what you're looking at on the left-hand side is the connectivity layer. And that connectivity layer allows data to flow into the system. These connectivity layers are extremely fast. They are not the bottleneck when it comes to pulling data in. Currently, right now, today in the UAS industry, the bottleneck is out on the 4G, 5G, that first mile of travel of data from the UAS to some sort of system to send the data up. But after that, once it's on the internet at large, vast amount of data can be pumped into things like Hadoop. So at the top, you see different types of transmission protocols that could be coming from UAS, everything from MQTT and RTMP to the good old-fashioned FTP. And in the middle, I'm demonstrating that there's a lot of data in the national airspace that's out there. There's primary and secondary radar, the emerging datacom, squawk codes, ADSB, and even voice data from towers and ATC regions can be collected and brought in to big data. And then finally, on the lower part, you see things like social media and the enterprise data warehouse. So social media is exactly as the name says. It's your Facebooks and your LinkedIn and things like that, and Twitter. That information can also be brought into your big data enterprise. And the enterprise data warehouse, well, that's just traditional data warehouses. That's inside the corporate America already. Now, coming up from the bottom, the parts in green, they come for free with any Hadoop system that you get. It's all of the data governance and security and masking and things like that that you would need. Moving up the chain, that next block of 6 orange boxes that are labeled, data integration governance and data clarification layer, those are typically custom built for your type of enterprise, but they're directly built from those green layers. So they don't represent a very large amount of effort. Moving up again, you see a series of boxes called raw data, repository, and then analytics. That's the heart of Hadoop. That is the heart of where data is stored, where data is staged, it's augmented, it's finally brought into this data lake, and then from there, analytics takes place. And then finally, at the very top, the orange box that says complex event processing is an optional layer that sits on top of Hadoop that allows you to bring data in memory and keep it moving, make decisions on the fly in near real time. So complex event processing is for fast data in motion, and then the boxes underneath it are more for long-term storage and batch processing. And then finally, the boxes in blue on the right side, those are the downstream systems that typically get fed by big data. So coming out of complex event processing at the end, typically at the top, typically what comes out of there are actions. Data comes in, you analyze the data on the fly, you make a decision to do something. In the boxes below it, the downstream side, you could have cloud systems that you might want to talk to, whether it's Amazon's AWS or Microsoft's Azure. You might have your drones as a service connections on that side, or you might be sending data to YouTube, Facebook, or any one of those cloud type environments or internet type environments that you want to send data to. In the next section, you have your typical visualizations. So you can kind of look at the data, see what the data is all about. The BI section allows you is where you typically accrue information about the data that you collected. You do roll up numbers, and you kind of give a status of what's going on. And then finally is the enterprise data warehouse again. So while we bring the enterprise data warehouse in on the left side, a lot of times the resultant path for data that comes into Hadoop is the enterprise data warehouse again. Not all of the data, because the enterprise data warehouse historically is just not big enough to hold that type of data, but it's where you would put the results. So where does this take us? Just, if you want to sit down and kind of get an idea of what big data technologies are out there, we have this chart, and a side note, I'm going to make this a full up presentation in the real one, but that's okay. No more pop-ups. So on the left side, you will see the kind of use case that you might use or look to implement, and the text in the parentheses is the big data equivalent. So if you're looking to get more information, we don't have time here to go into this, but you could look into those different technologies in the parentheses. So questions. What is big data Hadoop? What is it good for? What makes it good for large data sets? How does it actually work? And how does it apply to UAS? Okay, a real quick Hadoop 101. This is what a Hadoop system typically looks like. You have racks of computer equipments. You have racks of computers. Each computer in there is an independent, standalone, cheap commodity computer. And what's important to note here is for any one of these computers, they have some memory and they have some disk. Writing to their own memory is the fastest thing they could do. Writing to their own disk is one of the slowest things they could do. If you have a computer in a rack, take the rack on the left, for example, computer number 1, he could write to any other computer in that rack in a reasonably fast amount of time. Not as fast as writing to his own memory, but pretty darn fast. On the other hand, if the computer number 1 in column 1 wants to write to data in, let's say, computer number 1 in rack 3, then it has to write out to the core switch, go across down into the next rack, and write out to that computer. So much slower than writing to another computer on your own rack, but still faster than writing to a computer in your Moving on. Now, for Hadoop, there is this notion of triplage of data. So whenever you write a piece of data to a computer in Hadoop, it is automatically duplicated. And I'll demonstrate that. If you watch on computer number 1, you'll see a red dot appear in a minute. And notice what happens. That dot is then duplicated on, in this case, computer number 3 in the same rack, and then computer number 2 in the rack next door. If you write another piece of data out, in this case it's going to be computer number 1 on rack 3. Notice it writes it out to another computer, and then finally to a computer in a separate rack. So why do they do this? Because these are commodity computers, and it's assumed that the computers are going to fail at any time. Again, literally cheap, low-end, inexpensive computers. They tend to fail. They don't have backup CPUs, backup power supplies, backup disks, backup memory. They're low-end computers, So anytime you write a piece of data to a computer, that computer is going to assume that at any time he could have some sort of failure, so he makes a copy of that data. And the way it works is first you make a copy of the data to another computer in your own rack, because you know you could do that fairly quickly. Again, you're racing against the clock in case you should happen to die. And then you write it out to a computer in another rack. And why do you do that? Well, not only can any one rack, any one computer die, but an entire rack could go down. So if that should happen, you want the data written out to another rack. And there's a lot of secret sauce under the covers as to what you do in failure modes and things like that. As a side effect, it turns out your data is triplicated. And it can actually be more, but it's tripled throughout the enterprise. Now picture all of these computers have lots of data and a lot of data that's been written in multiple places. The way Hadoop works at its core is you spend a lot of time collecting data, which is these dots, that's the map part, and then at a certain time you say, okay, for whatever data you have on your particular computer, do some analysis work. And as you could see, computer number one in rack one, it has just so happens to have twice as much data as anybody else. So he's going to take, in theory, twice as long to get an answer. Meanwhile, the other two red dot computers don't have that much data, and they're probably going to get done first. So that's kind of a form follows function with Hadoop. The computers in the racks that have little data are probably going to get done first and beat computer number one to the punch. So there's a little gamification going on, a little bit of race condition that goes on to see who can get the answer fastest, which is kind of cool because who's to say that all of these computers in the racks have the same CPU and the same memory speeds? They're commodity computers. They're assumed that they're going to die over time and be replaced. You might even decide at some point to add more racks to scale out your solution. And when you do that, the commodity computer of the day might be just faster. And so you might have, a little bit of imbalance, but that's okay because that all adds to the secret sauce. Okay, so here we are in Las Vegas, and it's the card counting capital the card playing capital of the world. Let's say I want to write a program to count cards. How would I go about doing that? Well, let's say I have 20,000 cards in play at any one time, and I want to count how many kings at a given time, how many kings are in play. Now, just to give you a visualization, 20,000 cards is about 380 decks. And that would be a stack of cards about 20 feet tall. If I had a stack of cards 20 feet tall and I asked one person to count how many kings are in that deck, they would do it the old-fashioned way. They'd start at the top, they'd pull a card off, they'd look at it, and decide if it's a king or not. If it's a king, they'd put it in a separate pile, and then they'd go until they got all the way to the end. And then when they're done, they would pick up that smaller deck and count it. So in relational database terms, that smaller pile of cards is called the result set, and counting them is count star of a select kings. That would take a while for any one person to do or any one computer to do if you just scale up the numbers. How does it work with big data? Well, let's say now I have 200 people sitting in rows in like a classroom setting. And I say everybody in this row, in the first row, is rack number one. Everybody in that row is in rack number two, etc. As the cards are dealt, I would hand, for example, a card to the first person in the first row. He would get up, he would write down what kind of card he has, he'd get up, he'd walk to another person in that row and say, I have a king of spades. He'd walk back to his desk. It would take a little while to do that walk, not too bad. He'd then get up again and he'd walk to the front of the room, across the room, down another row to his other sister computer and say, okay, king of spades, and he'd walk back. That is the equivalent of the map part that we just talked about. It's fast to tell somebody else in your row what you have. It's a bit slower to walk around and tell the guy on the next row or a different row what you have. But what you've done now is you've spread the cards out to the same card to three different persons. Now, imagine you do that for all 20,000 cards. When you're done, on average, each person will have 100 cards sitting in front of them. So now if you say, I want to count how many cards are in play, each person will pick up their 100 cards. They will quickly go through it, just like the result set from a relational database. They will quickly count the number of cards they have, and they hold up that many fingers in the air for how many cards they have. God help the person who has more than 10 cards, but let's not worry about that. That is how Hadoop works. So, how does that apply to UAS? Let's say that you are looking to do pole rot examinations. Now, telephone poles, a lot of people don't realize this, they rot from the top down because rainwater collects on the top, the sun beats on them on the top, snow collects, ice collects. The top of telephone poles are the weak area. Now, let's take this a step further and say that, well, you might be doing this as your primary mission, which would mean you would fly a drone over to a telephone pole, take a picture, maybe turn it so you come in from a different angle, do all four sides, and then from the top down. Again, sun angles and things, you want to get all different sides. As you all know, that's a bit of a challenge. It's not overly difficult, but it certainly is a bit of work to, especially in windy conditions, to get a drone, get that telephone pole in place and take a picture. But what if it's a secondary mission? What if you are for, say, let's say, a package delivery company, and you are looking to head to a house and drop off a package? But you kind of scratch your head and say, there's other ways to make money in the world. Maybe we will set up an agreement with the different utilities out there, and as we fly past telephone poles, we'll create a database of poles that we have scanned and haven't scanned or reported on lately. And when we find telephone poles that are defective, we will send a message or a packet of information over to the utility company, say this pole is defective. And maybe you're not even doing pole rot. Maybe you're looking at tree limb incursion. So things like that you might be doing as a secondary process. That would be really cool to do. After all, in theory, let's say it's beyond line of sight flight. These drones are flying somewhat autonomously. I mean, you can't really have a person, if you really scale this out, let's take it to the future. People aren't going to be flying these things. They're going to be flying themselves. So therefore, you kind of want to do this, but you don't want people involved. So what are the big data asks? You want near real-time analytics. You don't need real-time. It's not like you're using this to stop the drone from flying into a telephone pole. But you want to kind of collect this data, and you want to make a decision in a reasonable amount of time, because there's no reason to sit on this and report at the end of the month. Although you could. That would be one option. But let's keep this as a real-time example. You want to apply a classification algorithm. You want to look at a telephone pole, and you don't want to so much do analysis on the pole to see if it's good or bad. You want to just kind of classify it and say, it's a tall pole, it's a short pole, it's defective or not, right? You want no human intervention. So, given that we have streaming video, not individual images, and let's say we have a database of 10,000 known good poles and 10,000 known bad poles. We want to, for every frame that comes in, if we see a telephone pole, make an autonomous decision and get that result into not only your enterprise, but the enterprise on the other end, in this case, the utility company. How would that work? Well, here's our big data block diagram again. Nothing really has changed here. We said we have a database of 10,000 good and bad poles. That would be pulled into big data, or Hadoop in this case, at one time. It's a one-time deal, 10,000 images, 20,000 altogether. Again, depending upon the size of your Hadoop cluster, that really could be anywhere from like 100 images on a node to 200, 500, something like that. It's not a big amount of data for Hadoop to process. Then after that, when the complex event processor starts, and remember I said the complex event processor is an in-memory process, so every time it starts, it has to pull everything in memory. It never wants to touch disk, it wants to be fast. So when the complex event processor starts, you would pull in these 10,000 known bad or good poles. Again, keep in mind, that just means in that Hadoop rack that we saw before, it's just going to read the data off disk and pull it into memory. And each node, when it does that, is only pulling in 100, 200 nodes at a time. Then the data starts flowing into the system. And when the data comes in, you would direct it directly to the complex event processor. The first thing it would do, it would tee the data so the raw video gets put into your data repository. And why? Well, because at some point you might want to go back and look at that data. If you find a bad pole, you're going to want to be able to go back to the data and say, hey, this is where we saw the bad poles in this geolocation, and this is what it looked like. There's other reasons why you might want to save the data. Let's say you're a package delivery company, and as a cool service, maybe you want to let somebody see the high-speed video of the path that the package took to get to their house. Maybe there's other good reasons why you'd want to do it, but again, you probably will want to save this data, if not forever, for a while. If not for no other reason than repudiation, or maybe somebody claims that you flew over their house and it was your company that did it. You want to be able to pull up the video and say, well, this was that package delivery. We never flew over your house. As that data, though, goes through the complex event processor, you want to look at the telephone poles as it goes by and make a decision if you have a good pole or a bad pole. If you find a bad pole, you want to generate a notification and store it in the data lake. Again, you're going to want to be able to come back and show somebody where the bad pole was. Next, you're going to want to take an action. If the utility is a message-based type of entity, like if they are an MQ or some other type of JMS-style message house, you're going to want to generate a message that you found the pole, send them the information, and fire that message off. You're then going to want to take that information and write it out to your enterprise data warehouse, and possibly even theirs if you have an electronic commerce type of connection. And then finally, you're going to want to create a workflow. No humans involved until a pole is found. And then in that case, the workflow gets generated that says, we found the pole on this date. We need to send out a bill. We need to make sure that the bill gets paid in this amount of time, and therefore a workflow needs to get generated. Again, that doesn't mean humans get involved. They would only get involved when something in the workflow falls out of sync, like you never get paid for it. Of course, there's this one little thing about identify defective poles. And that sounds a lot like, and then a miracle happens. So what's that all about? Well, remember our Hadoop cluster. So we have these racks of computers, and they all have these defective and good known poles on them. And let's just say there's 100 per computer. So if any image comes in, any one of these computers would look at it and decide, does this particular image fit what we think are good poles? Do we think it would fit bad poles? Or is it something in the middle, aka there's no pole involved at all, right? So the first thing you do is the images, the video would come in to the complex event processor. And for people who might not realize it, video is not a series of JPEG images. It's actually, picture it, a JPEG image, and then the next one is information about how the first JPEG image changed, followed by information on how the next JPEG image changed. So at any one time, a frame is not what you think it is. It's kind of a space-saving reduction of the images that you have seen. So the first thing you'd want to do is take these frames and convert them to JPEG images, frame at a time on the fly. Then when you have any one frame, you now have, in theory, a picture of a telephone pole. You're going to want to take that image and you're going to want to send it out to your Hadoop cluster. Basically, that picture would be copied to every single node in your network. So if you have a 50-node Hadoop cluster, you would have to make 50 copies of it out on the servers. And of course, if it's the rule of 3, anytime you write a picture out to one node, it's going to make 2 more copies, so you can have 150 pictures. And the numbers scale up from there. Very doable, not a hard thing. Then you're going to want to do the classification algorithm. Now, classification algorithms, they're kind of a dime a dozen nowadays. It is not hard at all to take a picture especially for a given type of application, be it a telephone pole, facial recognition, things like that, and say, here's an image, which one does it match? Fairly straightforward process to say, here's a picture of a telephone pole, does it match the good poles or the bad poles? Notice everybody kind of comes up with an answer. Some say it's 92% sure, others say it's 85, but what you could see just using your eyes that in general, a lot of people, a lot of computers are thinking that this is a bad pole. So you would want to roll up the results and then basically calculate the consensus and say, hey, in this particular frame, that pole is bad. And that information is the notification that would go down into your big data system and say, yep, we have a bad pole in this frame. And then again, you'd want to roll that up and say, like from frame X to frame Y, we're seeing images of a bad telephone pole. Another use case that you could use with big data is news gathering. So in general, you would have the video coming in and going to your complex event processor and just spitting out the other side into your content delivery network. Now, the newsies are going to sit out there and say, okay, Ken, we do this all the time. We collect video. It doesn't have to be from drones. We collect video from all types of sources, and we bring it into our own networks, and we do a little bit of live monitoring. So like we're looking for things. We want to have a little bit of a delay, and then after that delay is over, we write it out to our content data network. Now, it's content delivery network. Now, the purpose for that is, you don't want to be doing a live feed of something going on in the news, and then the next thing you know, somebody gets shot or there's an accident or something horrific happens. You want to be able to have a few seconds where you can view it and then cut it off. This replicates that exactly. Why use big data? Is it that you have a big data hammer and everything looks like a big data nail, so you're using it? No, because we could do a lot with big data. So for example, let's say you're taking in Twitter feeds and it comes into your big data system. We can read those feeds and do sentiment analysis on it. And the result of that sentiment analysis can then be fed back out to the UAS to make decisions. For example, you are flying over a football stadium, it's the end of the game, and you're just doing a live report on the end of some important football game. And then the next thing that's happening separately in Twitter is they're starting to crop up messages about a fight in the parking lot or some sort of terrorist activity. A computer can pick up on that much faster than humans can generate sentiment, figure out where the geolocation is, and then send notifications, whether it's automated to send the drone somewhere else or an alert message that go to the people recording it and tell you to steer the drone somewhere else. So this is a case where data that comes in and flows through the big data system can then be augmented with sentiment analysis to redirect it somewhere else. The final use case that I want to go over is kind of near and dear to me. It's the shared manned-unmanned space. So sticking with this premise, we're in the future. It's beyond visual lines of sight. We're allowed to fly over crowds. We're doing all kinds of things with drones. We're delivering packages. We're delivering burritos. Drones are being used to do house inspections. They're doing cell phone towers. They're just out there like little worker bees doing all sorts of things. The drones are staying below the 400-foot level. The planes are staying above 800 feet. And we have our buffer in the middle. Everything's great. I'm flying along on my airplane, and I start to smell smoke. I'm immediately start scanning my instruments, trying to figure out, do I have an electrical fire in the plane, or is it a fuel-fed fire in the cowling? I look out at the cowling, and I see the paint start to bubble. And that kind of tells me, okay, I have an engine fire. I start going through my memory checklist of what I have to do. I'm getting very busy. I have to decide, is this the kind of fire where I just want to shut the engine off right now and put it into a dive so I can maybe blow out the fire? Do I want to just shut the fuel off first and let whatever fuel's in the engine continue to burn off, but at least then the fire, the source of the fire, the source of the fuel is gone, and then I do my dive? Am I high enough to dive? Maybe I don't have the altitude to make this dive. There's a lot going on. The bottom line is my cockpit, in my cockpit, going to be very, very busy. Most likely, I will have this foresight to at least key my mic and say, Mayday, Mayday, Mayday. And that's important because I am in the national airspace and I'm sharing that space with other aircraft, and happens to be now I'm sharing it with UAS. By saying Mayday, 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 I have told the local controller, this is effectively now my airspace. I am going to control what happens in this airspace. You are going to get every other aircraft, including drones, out of my way. Now, getting other aircraft out of the way isn't so difficult. Even if I only say Mayday, 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 they know I have a problem. They're probably going to come back and say, 5312 Sierra, acknowledge you're declaring an emergency. Please state the nature. I might not answer that. I am busy. They get it. They know where I am. They will start to get airplanes out of my way. They're going to assume two things. I'm either going to do a forced off-field landing, or I'm going to try to make it to the nearest airport. They're going to work on that premise until they hear otherwise. Drones create a bit of a problem. So what do we do about drones? Well, there's no reason that big data can't be monitoring ATC voice communications throughout the country, every frequency. We know where the frequencies are. We know what regions on the sectional that they apply to. Once you get a Mayday, 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 sentiment analysis should be able to pick that up, and they immediately know in a certain sector something bad is happening, and basically drones need to leave the area. Drones that are about to enter the area need to be redirected out. Drones that are in the area are going to be told a couple of things. If you're close to delivering your package, deliver it and land. Maybe other drones will be told, hey, go to this cell phone tower that has a docking station and dock and stay there. Other drones maybe will be told to turn and leave. It's a big area. It's going to affect a lot of drones. We might say in the Internet of Things, it might look and see that there is a delivery truck heading down the highway with docking stations on the roof for drones. An instruction might be sent to that delivery truck to pull over immediately, and drones would be redirected to land on the roof of that truck. So there's a lot that can be done when that happens. But let's say I actually come back now and using primary, secondary radar, maybe by squawk code or ADSB, they get a really good fix on where I am, and then I come back and say, 1-2 Sierra, engine fire, no power, forced off field landing. Now that big area that all the drones are being forced out of actually now kind of gets shrunk down, because with the information that the FAA has, they know what kind of plane I have. They know my theoretical glide slope. They know how far I can travel, and they can send more detailed information. They might now tell some drones that were on the periphery of that to take off from those cell phone charging stations so other drones can go in there. But the beauty is, with a system like this, things can be done to ensure the safety between manned and unmanned aircraft and allow us to share the environment. So, in conclusion, there's a lot that needs to be done yet for the scenarios I described to happen. Certainly, the first mile is an issue. If you have a drone flying around taking 4K video, it's an issue right now to try to get that data out in a reasonable amount of time. But that's being addressed. The new 5G networks will certainly bring a lot to the table, and there are other technologies on the way. So, security with drones historically has been a little bit abysmal, but that's also easily addressed, and things like that will take care of itself. The bottom line is UAS have the ability to generate vast amount of data. Big data was designed to process that data, and the two are going to come together and meet, because at the end of the day, it's really not about the mission, it's about the data. Thank you. I hope you enjoyed this presentation.